This search takes about 4 seconds. You open GitHub, type a specific query, and you get back a list of repositories, public repositories, belonging to real companies that contain files with database passwords, API keys, and service credentials sitting in plain text. Not because anyone broke in, not because any vulnerability was exploited, because a developer committed a config file they forgot to exclude, or a CI pipeline dumped its environment variables somewhere they shouldn't be, or a Docker image was built with secrets baked into a layer that nobody thought to check. The credentials are real. The accounts they belong to are still active, and in many cases, those accounts have access to production systems, because they were service accounts, created to let one system talk to another, and nobody thought carefully about what happens if the key walks out the door. This is not a story about human accounts being phished, or human passwords being guessed. The humans aren't involved at all. The target is something most security teams spend very little time thinking about: the credentials that belong to machines. And the reason attackers increasingly go after these is simple. Machine credentials are more numerous, less monitored, longer lived, and more powerful than most people realize, because the organizations that issue them rarely treat them with the same seriousness as human credentials. Let's look at exactly why that is, and what it looks like when it goes wrong. When a person logs into a system, there is an interactive moment, a prompt, a response. Someone is present and engaged with the authentication event. When a machine authenticates, a service calling an API, a pipeline deploying code, a monitoring agent checking a database, there is no interactive moment. The credential is stored somewhere, retrieved automatically, presented without any human involvement, and the authentication succeeds or fails without anyone noticing either way. That difference, interactive versus automated, observed versus unattended, is what makes machine credentials structurally different from human ones. They take a few different forms. API keys are static strings with no expiry unless someone explicitly rotates them. Certificates are more structured, bound to a specific identity through a public key, but they expire and need renewal. Service account tokens are issued by platforms, cloud providers, Kubernetes clusters, often short-lived and automatically refreshed. Workload identity is the newest model, where the platform itself attests the credential rather than the workload carrying a secret at all. The security profile of each is different, but they share something important. In most organizations, none of them are managed with anything close to the attention applied to human credentials. No MFA, no regular review, no offboarding process when the workload they belong to is shut down. And in most organizations, there are far more of them than there are human accounts, often by an order of magnitude. When attackers target machine credentials, they use one of 4 patterns, and each one exploits a different aspect of how these credentials are typically mismanaged. The first is simple exposure. The credential exists somewhere it shouldn't. The GitHub search from the opening is the obvious case, but the surface is much wider than public repositories. Environment variables printed into application logs, Docker image layers that contain build time secrets, configuration files committed to internal repositories that have broader access than intended, credentials hard-coded into scripts that were written for a one-off task and then left running on a schedule for 3 years. What makes exposure particularly damaging for machine credentials, compared to, say, an exposed human password, is what tends to sit behind them. A human password gives you access to one person's account. A service account credential for a CI/CD pipeline might give you the ability to write code into production deployments. A cloud provider API key tied to an infrastructure automation role might give you the ability to create new users, modify firewall rules, or access every storage bucket in the account. The credential looks unremarkable in a repository. What it unlocks often is not. The second pattern is privilege accumulation. And this one is less about finding credentials and more about what happens after an attacker already has one. Service accounts are created for a specific purpose. Let this service do this thing. But over time, as requirements expand and teams change, access gets added rather than redesigned. The service that needed read access to one database now has read-write access to 3. The deployment pipeline that needed to push to one environment now has production access across the entire infrastructure. Each individual permission addition felt reasonable at the time. Nobody went back to ask whether the original scope still made sense. The result is a service account whose actual access is dramatically larger than any single person could describe accurately. For an attacker who gains control of that credential, this is not a bonus, it is the whole point. The misconfigured overprivileged service account is a reliable path to lateral movement and privilege escalation, precisely because the defenders often do not know what the account can actually do. An attacker with time can figure it out by probing. The defenders are playing catch-up on a scope they never clearly defined. The third pattern targets orphaned credentials, machine identities that have been abandoned without being revoked. A microservice gets replaced by a newer version. The old service is shut down. The service account it used is not decommissioned because decommissioning machine credentials is a manual process in most organizations, and the team has already moved on to the next thing. 6 months later, that service account still exists, still has valid credentials, and still has whatever permissions it accumulated during its active life. From the outside, an orphaned credential is indistinguishable from an active one. The authentication succeeds. The token is valid, the permissions are real. There is no flag that says this account has not been used in 4 months and the service it belonged to no longer exists. Attackers, who gain access to a credential store through a breach, through an insider, through an exposed backup, will often specifically hunt for orphaned accounts. They tend to be the most permissive because they were never cleaned up, and the least monitored because nobody is looking for activity on a service that was supposed to be shut down. The fourth pattern is the most architecturally interesting and the one that is hardest to defend against without rethinking how service-to-service trust works. In a microservices environment, services authenticate to each other. Service A holds a credential that Service B trusts. Service B holds a credential that Service C trusts. These trust relationships are the plumbing of the system, necessary, everywhere, and rarely drawn on a diagram that anyone looks at. An attacker who compromises a single machine credential does not necessarily stop at what that credential can directly access. They look at what services trust it, what those services can access in turn, and whether they can use that chain to reach something more valuable than their starting point. This is lateral movement using legitimate credentials. Every step in the chain is an authenticated request. Every hop looks to each individual service like a normal interaction from a known peer. No single system has a view of the full chain being traversed. The attack is only visible if someone is watching the aggregate pattern across all systems simultaneously, which in most environments, nobody is. Machine credentials generate enormous volumes of normal, legitimate traffic. A service might make thousands of authenticated calls per hour as part of its regular operation. An attacker using a stolen service credential generates traffic that is structurally identical to that normal volume. Same source, same authentication mechanism, same format. Human account compromise tends to produce detectable anomalies. A login from a new country, an unusual time of day, a device not seen before. These signals exist because human behavior has a shape, and departures from that shape are visible. Machine behavior has a shape too, but it is harder to baseline. Services run on schedules, respond to events, scale horizontally in ways that make traffic patterns variable. An attacker who understands what a service normally does can stay within that envelope, requesting access at expected times, in expected volumes, to expected endpoints, and generate nothing that a rules-based detection system would flag. The practical consequence is that machine credential compromise tends to have a longer dwell time than human account compromise. It is found later, which means more lateral movement, more access, more damage by the time detection happens. Machine credentials are not exotic targets that only sophisticated attackers go after. The GitHub search at the start of this video is genuinely how some breaches begin, not with a 0-day, not with a nation-state actor, but with a 4-second query that returns credentials someone forgot about. The gap is not technical. The tooling to manage machine credentials well exists. The gap is that most organizations apply human-shaped thinking to non-human identities, periodic reviews, manual processes, attention triggered by visible events, and machine credentials do not generate visible events. They just sit there, accumulating permissions, until something uses them.